From the theory that we discussed so far, we can say that to find Laplace transform of a generic function f of t, which is one-sided, we can use the definition of Laplace transform, that is Laplace transform of f of t is equal to integral 0 to infinity e power minus st f of t dt, or we can find the Laplace transform of f of t using properties of Laplace transform or by inspection of f of t. Similarly, to find inverse Laplace transform of f of s, which is equal to Laplace transform of f of t. So here we need to find f of t. We see that inverse Laplace transform can be found by using properties of Laplace transform or by inspection or by partial fractions. Please note that we would demonstrate all of these, that is finding Laplace transform of f of t using different methods and finding inverse Laplace transform of f of s using different methods will be demonstrated in subsequent examples. Now let us find some of the now let us solve some of the problems. As per the problem, we need to find inverse Laplace transform of s square plus 2s plus 2 divided by s plus 1 whole cube. We know that s square plus 2s plus 2 divided by s plus 1 whole cube can be written as s plus 1 whole square plus 1 divided by s plus 1 whole cube, because s plus 1 whole square plus 1 is equal to s square plus 2s plus 2. This can be written as 1 by s plus 1 plus 1 by s plus 1 whole cube. So from this we can say that L inverse of s square plus 2s plus 2 divided by s plus 1 whole cube can be written as L inverse of 1 by s plus 1 plus L inverse of 1 by s plus 1 whole cube. We know that L inverse of 1 by s plus 1 is e power minus t into u of t. Also we know that L inverse of 1 by s cube is equal to t square by 2. From this, L inverse of 1 by s plus 1 whole cube can be written as t square by 2 multiplied by e power minus t multiplied by u of t. This is because of the property that Laplace transform of e power minus at f of t is equal to f of s plus a. From this, the required inverse Laplace transform can be written as e power minus t multiplied by 1 plus t square by 2 multiplied by u of t. So this is the L inverse of given f of s. Now let us solve another problem, as per which there is a signal f of t given as shown, where f of t is 1 from 0 to 2 and it is minus 2 from 2 to 4. Also f of t is 2 from 4 to 6, then f of t is minus 2 from 6 to 8. So this is the given f of t. Please note that for t doesn't belong to the case of 0 to 8, f of t is 0. From this we can write that f of t is equal to u of t minus 3 into u of t minus 2 plus 4 into u of t minus 4, sorry, yeah, plus 4 into u of t minus 4 minus 4 into u of t minus 6 plus t 2 into u of t minus 8. So from the given f of t, by writing the f of t in terms of the unit step function u of t or delayed versions of unit step function, we get that f of t is equal to u of t minus 3 into u of t minus 2 plus 4 into u of t minus 4 minus 4 into u of 2 minus 6 plus 2 into u of t minus 8. We know that Laplace transform of u of t is equal to 1 by s. We also know that Laplace transform of u of t minus a is equal to e power minus as multiplied by 1 by s. From this, we can write that Laplace transform of f of t is equal to 1 by s multiplied by 1 minus 3 into e power minus 2s plus 4 into e power minus 4s minus 4 into e power minus 6s plus 2 into e power minus 8s. This is obtained from the given from the f of t obtained here and by using the Laplace transforms of some of the standard functions. So we can say that Laplace transform of f of t is equal to 1 by s multiplied by 1 minus 3 into e power minus 2s plus 4 into e power minus 4s minus 4 into e power minus 6x plus 2 into e power minus 8s. Now let us look into another problem as per which there is a continuous time LTI system given which is represented by the IO relation y of t is equal to 1 by t multiplied by integral t minus t by 2 to t plus t by 2 x of tau d tau. We need to find the impulse response h of t of this LTI system. We see that for the given LTI system, y of t at any instant t is obtained by integrating x of t over the range of minus t by 2 to plus t by 2 about t. Also please note that this integration is weighted by 1 by t. From this we can see that y of t is actually a convolution of x of t and h of t, where h of t is a pulse of width capital T, means it is present from minus t by 2 to plus t by 2, and the pulse is of height 1 by t. From this we can say that the impulse response of the system is h of t is equal to 1 by t multiplied by u of t plus t by 2 minus u of t minus t by 2. So this is the impulse response of the given LTI system. Now let us look into another problem. as per which we need to find the Laplace transform of 1 by t multiplied by sine of t ut. We know that the Laplace transform of sine of t multiplied by ut is equal to 1 by s square plus 1. We also know that Laplace transform of 1 by t multiplied by f of t, where f of t is one-sided, is equal to integral s to infinity f of s ds, where f of s is Laplace transform of f of t. From this, we can write that Laplace transform of 1 by t multiplied by sine of t ut is equal to integral s to infinity Laplace transform of sine of t ut is equal to 1 by s square plus 1. So this should be substituted here, then ds. But we also know that this definite integral can be obtained as shown. That is, integral of 1 by s square plus 1 ds is equal to tan inverse s, and the limits are infinity and s. So this can be simplified as tan inverse infinity minus tan inverse s. This is equal to pi by 2 minus tan inverse s. From this we can say that Laplace transform of 1 by t sin t u of t is equal to pi by t minus tan inverse s. Now let us look into another problem as per which we need to find the Laplace transform of t into e power minus at u of t. We know that the Laplace transform of t into u of t is equal to 1 by s square. We also know that the Laplace transform of t into e power minus at u of t would be equal to 1 by s plus a whole square. This is based on the property that Laplace transform of e power minus at f of t is equal to f of s plus a, where f of s is the Laplace transform of f of t, and also please note that f of t is one-sided function. So from this we say that Laplace transform of t into e power minus at u of t is equal to 1 by s plus a whole square. Now let us look into another problem as per which it's given that Laplace transform of x of t is equal to x of s. Based on this, we need to find the Laplace transform of x of 2t. We know that Laplace transform of x of t can be written as integral 0 to infinity e power minus st f of t dt. Sorry, x of t dt. This is assuming that x of t is a one-sided function. From this, we can write that Laplace transform of x of 2t is equal to integral 0 to infinity e power minus st multiplied by x of 2t dt. Upon substituting 2t is equal to p, we see that 2 dt is equal to dp. Also, at t equal to 0, p would be equal to 0. As t tends to infinity, p also tends to infinity. From this, we can modify the integral as integral 0 to infinity e power minus s p by 2 multiplied by x of p dp by 2. So this can further be simplified as 1 by 2 multiplied by integral 0 to infinity x of p multiplied by e power minus s by 2 p dp. So we know that the term that is marked just now is equivalent to x of s by 2. From this we can write that Laplace transform of x of 2t is equal to 1 by 2 multiplied by x of s by 2. Now let us look into another problem in which we need to find the inverse Laplace transform of 1 by s plus 1 multiplied by s plus 2. We know that the term 1 by s plus 1 multiplied by s plus 2 is not of standard form. This can be brought into a standard form by splitting into partial fractions. So the term becomes a by s plus 1 plus b by s plus 2. So this can be written as a into s plus 2 plus b into s plus 1 divided by s plus 1 into s plus 2. Upon equating the numerator 1 with a into s plus 2 plus b into s plus 1, we get that a plus b is equal to 0 because the term containing s is absent in the numerator. Also, we can say that 2a plus b is equal to 1. Upon substituting a is equal to minus b, we get that b is equal to minus 1 and a is equal to 1. From this, we can write that L inverse of 1 by s plus 1 into s plus 2 is equal to L inverse of 1 by s plus 1 minus 1 by s plus 2. We know that L inverse of 1 by s plus 1 is equal to e power minus t u of t, and L inverse of 1 by s plus 2 is equal to e power minus 2t u of t. From this we see that L inverse of f of s is equal to e power minus t minus e power minus 2t multiplied by u of t. Now let us look into another problem as per which we need to find the inverse Laplace transform of 1 by s square plus 1 multiplied by s plus 1. Here also we see that the term 1 by s square plus 1 multiplied by s plus 1 is not of standard form. So this can be written in partial fractions form as as plus b divided by s square plus 1 plus c divided by s plus 1. So this upon simplification becomes as plus b into s plus 1 plus c into s square plus 1 divided by s square plus 1 multiplied by s plus 1. Upon equating the numerator 1 with as plus b multiplied by s plus 1 plus c into s square plus 1, we get that a plus c is equal to 0 because the term containing s square is equal to 0, and b plus a is also equal to 0 because the term containing s is also not present. Also, b plus c is equal to 1. Upon simplification, we get that a is equal to minus 1 by 5. That is by solving the three equations that we obtained, and b is equal to 2 by 5, c is equal to 1 by 5. Sorry, b should be equal to. Now let us look into another problem as per which we need to find the inverse Laplace transform of 1 by s square plus 1 multiplied by s plus 1. The term given, that is 1 by s square plus 1 multiplied by 1 by s plus 1, sorry, multiplied by s plus 1 is not of standard form. So upon splitting this into partial fractions, we get that the given f of s is equal to as plus b divided by s square plus 1 plus c divided by s plus 1. Upon simplifying this summation, we get that as plus b multiplied by s plus 1 plus c into s square plus 1 divided by s square plus 1 into s plus 1 is equal to the given f of s. Upon equating the numerator, as the terms containing s square and s are absent, we get that a plus c is equal to 0, b plus a is equal to 0, b plus c is equal to 1. Upon simplifying these three equations, we get that a is equal to minus half, b is equal to half, and c is equal to half. Upon substitution, we get that L inverse of 1 by s square plus 1 multiplied by s plus 1 is equal to minus of s minus 1 divided by 2 into s square plus 1 plus 1 by 2 into s plus 1. This is L inverse of. So this can further be simplified as minus sorry minus half multiplied by L inverse of s by s square plus 1 plus half multiplied by L inverse of 1 by s square plus 1 plus 1 by 2 multiplied by L inverse of 1 by s plus 1. We know that L inverse of s by s square plus 1 is equal to cos t u of t, and L inverse of 1 by s square plus 1 is equal to sin t u of t, and L inverse of 1 by s plus 1 is equal to e power minus t u of t. Upon substitution, we get that the inverse Laplace transform is minus 1 by 2 cos t plus 1 by 2 sin t plus 1 by 2 e power minus t as a whole multiplied by u of t. So this is the inverse Laplace transform of given f of s. Now let us look into another problem as per which there is a signal f of t given as shown in the figure. F of t is an impulse train with periodic impulses separated by capital T. And please note that the impulse has a magnitude of 1. If f of t is given as shown, we need to find Laplace transform of f of t. We know that if f of t is a function which is periodic with period capital T, Laplace transform of f of t can be written as 1 by 1 minus e power minus st integral 0 to capital T e power minus st f of t dt. So the integral is the Laplace transform over one period. We know that in one period or in the first period, f of t has a value of 1 only at t equal to 0 because of the impulse at that instant. From this we get that Laplace transform of f of t is equal to 1 by 1 minus e power minus st integral 0 to t e power minus st multiplied by delta of t dt. The given are the integral marked is equal to 1. From this, we can say that the Laplace transform of given f of t is equal to 1 by 1 minus e power minus st.